4 million people live on top of a fault system that just failed its own risk assessment. Not because the science was bad, because the fault was too short. There's a rule buried in the way the United States calculates earthquake hazard. If a fault doesn't stretch far enough across the map, it gets left out of the model entirely, no matter how often it ruptures. In Seattle, that rule just excluded a fault system quietly breaking every 3.5 centuries, and it broke most recently only 200 years ago. Let that sit for a second, because it isn't a hypothetical. It's a peer-reviewed finding, published in January 2026, built from soil samples, tree rings, magnetic surveys, and years of digging trenches across a city most people think they already understand the risks of. Seattle sits in the collective imagination as a Cascadia city. Ask almost anyone in the Pacific Northwest what the big earthquake threat is, and they'll say the same thing. The subduction zone offshore, the one capable of a magnitude 9, the one that shakes for minutes instead of seconds and sends a wall of water toward the coast. That threat is real, but it turns out to be only part of the story, and maybe not even the most urgent part. Seattle proper is home to just over 700,000 people. Widen the lens to the greater Puget Sound region, and the number climbs past 4 million. This is the economic core of Washington state, the biggest port on this stretch of coastline, home to Amazon's headquarters, Microsoft's sprawling campus in Redmond, and the ferries that cut across the Sound daily carrying commuters between islands and the mainland. It's a region built on some of the most productive tech wealth in the country, layered on top of some of the most complicated and least understood geology in North America. And for decades, that geology has been simplified into 2 headlines. Cascadia is the big one, and it's coming eventually. And the Seattle Fault, the fault that runs directly beneath downtown, produces massive earthquakes only once every several thousand years, so it isn't the immediate concern. Both of those headlines are still technically true, but a study published in the GSA Bulletin in January 2026 makes the case that they are dangerously incomplete. The lead scientist behind that study is Stephen Angster, a research geologist with the United States Geological Survey's Earthquake Science Center in Seattle. His specialty is paleoseismology, which is a way of saying he studies earthquakes that happened long before anyone was around to record them with instruments. There are no seismographs from the year 900. There are no newspaper articles describing a magnitude 7 earthquake in the 1820s. Instead, paleoseismologists read the ground itself. They look at soil layers for signs of sudden disruption. They study drowned forests at the bottom of lakes, where a sudden earthquake triggered flood buried entire stands of trees so quickly that the wood never fully decayed. They use radiocarbon dating and tree ring analysis to pin down almost exact windows of time when the ground moved. It is slow, painstaking, forensic work, piecing together a crime scene that is sometimes 11,000 years old. To understand why Angster's newest findings matter, you have to understand the fault system he was studying. The Seattle Fault Zone is not a single crack in the earth. It's a network, an east-to-west trending system stretching roughly 75 kilometers from the foothills of the Cascade Mountains in the east, straight through downtown Seattle, out past Bainbridge Island toward the Olympic Peninsula in the west. It runs beneath the stadiums where the Seahawks and Mariners play. It runs beneath the historic brick buildings of Pioneer Square, beneath the waterfront where tourists photograph the ferries and the mountains in the distance. This is not some remote offshore hazard. This is a fault system sitting directly under one of the largest metropolitan areas on the West Coast. Geologists first started paying close attention to the Seattle Fault Zone in the early 1990s, and what pulled them in were strange details. Odd gravitational readings, stair-step-shaped rock formations along the shoreline called marine terraces, the kind of feature you'd expect if the coastline had been thrust upward suddenly at some point in the past. And growing physical evidence of an ancient tsunami that had swept through Puget Sound roughly 1,000 years earlier. As researchers dug deeper, quite literally, the picture that emerged was staggering. Around the year 923, a magnitude 7.5 earthquake ruptured the main Seattle Fault. The ground surged upward. Shorelines around what's now called Restoration Point were thrust up by as much as 8 meters, nearly 26 feet, almost instantly, the ocean pulling back as the land physically lifted out of the water. That kind of event doesn't just leave a mark, it leaves a fingerprint spread across an entire region. Sediment cores from the era contain sandy layers consistent with a tsunami surge. Landslides triggered by the shaking dammed streams and flooded forests, drowning stands of Douglas fir trees whose trunks are still preserved at the bottoms of lakes today. In 2023, a research team led by Brian Black at the University of Arizona used those drowned trees to date the earthquake with remarkable precision. By matching the pattern of growth rings in the dead wood against a reference chronology spanning 1,300 years, they narrowed the earthquake's timing down to a 6-month window, somewhere between the fall of the year 923 and the spring of the year 924. And then the tree rings revealed something nobody expected. The same narrow death window showed up in trees drowned along the Saddle Mountain Fault, a completely separate fault system slicing across the Olympic Peninsula near Lake Cushman, dozens of miles away. Two faults, separated by significant distance, appeared to have ruptured at almost exactly the same moment. Either they broke together in one enormous composite earthquake somewhere around magnitude 7.8, or they broke in two closely spaced events, one around magnitude 7.5 and another around 7.3. Either scenario is difficult for modern hazard planning to digest, because current models generally don't account for multiple faults rupturing together in a single cascading event. A magnitude 7.8. Earthquake releases dozens of times more energy than a magnitude 6.7, and researchers now believe the year 923 event was likely the most intense seismic episode to strike Puget Sound since the end of the last ice age, roughly 16,000 years ago. For a long time, that was where the story of the Seattle Fault mostly stopped. Scientists knew the main fault could produce something catastrophic. They also estimated that the main fault's recurrence interval, meaning the average time between events of that scale, was somewhere north of 5,000 years. From a pure probability standpoint, that offered a strange kind of comfort. The worst-case scenario existed, but it was distant, statistically speaking, something for a future many generations removed from the buildings standing today. Except the Seattle Fault Zone was never just the main fault. It's a mesh of smaller fractures branching off the primary structure, absorbing pieces of the same tectonic stress that builds across the region. As the crust between Portland, Oregon, and Vancouver, British Columbia gets squeezed and rotated by the forces offshore. The main fault gets the attention because it's capable of the biggest single event. The secondary faults, shorter, less dramatic on paper, had barely been studied until fairly recently. That is precisely where Stephen Angster's new research comes in. His team focused on two specific secondary structures within the larger Seattle Fault Zone, the Lytle Beach Fault and the Vasa Park Fault. These are shallow, south-dipping structures sitting within what geologists call the hanging wall of the larger fault system, meaning they sit above the main fault plane and share a general orientation with it. But they're shorter, and their behavior had never been carefully documented. The reason nobody had studied them closely for years comes down to a bureaucratic detail with enormous consequences. The National Seismic Hazard Model, the tool the federal government uses to calculate earthquake risk across the entire country, has a minimum length requirement for any fault it includes. If a fault doesn't meet that length threshold, it gets excluded from the model, on the assumption that shorter faults are too small to produce earthquakes large enough to matter. The Lytle Beach Fault and the Vasa Park Fault don't meet that threshold, which means, until now, they simply weren't part of the national conversation about risk in Seattle. Not in the building codes, not in the insurance calculations, not in the emergency planning documents mailed out to residents. Angster wanted to find out whether that omission was a mistake. His team used a combination of tools to investigate: magnetic surveys to map subsurface structures invisible from the surface, LiDAR, a laser-based mapping technology capable of stripping away vegetation digitally and revealing subtle ridges called fault scarps, the marks where the ground has ruptured in the past. They dug trenches directly across the suspected fault lines, carefully logging every layer of exposed soil for signs of disruption, and used dating techniques, radiocarbon analysis, and tree ring chronology among them, to pin down when those disruptions had happened. What they found did not match the assumption baked into the national model. The trench record for the Lytle Beach Fault revealed evidence of two separate surface rupturing earthquakes. The older event happened somewhere between roughly 11,240 and 10,430 calibrated years before the present, near the tail end of the last ice age. The younger event happened after the year 1663, and the evidence points most strongly toward the early 19th century. Read that again, because it's the detail that changes everything. Not 11,000 years ago, not 5,000 years ago, the early 1800s. That's within living memory of early European settlement in the Pacific Northwest. That's recent enough that people were almost certainly living in the region when the ground moved, even if nobody wrote it down in a form that survived. The Vasa Park Fault told a similar story of independence. These secondary structures weren't simply smaller echoes of the main fault, waiting passively for the big one to trigger them. They were capable of accumulating their own stress and rupturing entirely on their own schedule. When Angster's team compiled the full picture, drawing in previous paleoseismic data from other secondary faults across the zone, the recurrence interval that emerged was striking. Roughly one earthquake every 350 years across the last 2,500 years. Compare that to the main fault's interval of more than 5,000 years. And you're looking at a system rupturing something like 14 times more frequently than the event everyone had been trained to worry about. There was another detail buried inside that data that Angster specifically flagged as important. Activity on these secondary faults appeared to have increased over the past 2,000 years, not decreased. The earthquakes, as far as the record shows, have been happening more often as time goes on. As Angster put it in describing the surface rupture history of the zone, the last 2,500 years have been dominated by these secondary fault events, not by the rare, massive ruptures of the main fault. This isn't purely academic. Previous research had already shown that at least one of these secondary structures had produced an earthquake around magnitude 6.7, roughly comparable in size to the 2001 Nisqually earthquake that shook the region and caused more than $200 million in damage to Seattle alone. But there's a crucial difference between that comparison and what a secondary fault rupture beneath the city would actually look like. The Nisqually earthquake originated deep underground, more than 50 kilometers below the surface, and its epicenter sat roughly 60 miles south of Seattle near Olympia. A shallow crustal earthquake on a secondary Seattle fault, even one of a similar magnitude, would behave completely differently, because the energy would be released far closer to the surface and far closer to the city center. Shallower earthquakes tend to produce more violent shaking, more concentrated damage, and less warning time, because the seismic waves have less distance to travel before they reach the buildings sitting directly overhead. It's worth spending a moment on what the Nisqually earthquake actually did, because it's the closest real-world comparison available. On February 28, 2001, a magnitude 6.8 earthquake struck near Olympia. Even from that distance and depth, Seattle suffered significant damage. Unreinforced brick buildings in Pioneer Square in the Chinatown International District cracked and shed masonry onto the sidewalks below. The historic Cadillac Hotel required extensive structural restoration. The elevated Alaskan Way Viaduct, the double-decked highway that once ran along the waterfront, sustained damage serious enough to eventually force its replacement with a new tunnel. 31 buildings were red-tagged as unsafe. More than 1,000 were yellow-tagged, meaning restricted access. Total damage across the region exceeded $2 billion, and that was an earthquake, originating deep underground, 60 miles away. Now picture something similar rupturing directly beneath downtown, at a fraction of that distance and depth. This is where geology collides with the physical reality of how Seattle was actually built. Large portions of the city sit on a mix of glacial deposits and artificial fill, laid down during rapid urban expansion in the late 1800s and early 1900s. The Duwamish Valley, Sodo, Georgetown, parts of South Park, much of the industrial waterfront corridor. These neighborhoods rest on loose, saturated soils layered over older, more stable deposits. During strong shaking, that kind of soil can undergo liquefaction, a process where trapped water pressure spikes so dramatically that solid ground effectively behaves like a liquid. Buildings tilt, roads buckle, underground infrastructure, water mains, sewer lines, gas pipes can shear apart or separate entirely. In extreme cases, structures can sink into ground that no longer behaves as a solid foundation. Roughly 15% of Seattle's total land area carries meaningful liquefaction risk, and much of that vulnerable ground sits directly along the trace of the Seattle fault system, precisely where a shallow crustal rupture would generate its strongest shaking. Then there's the building stock itself. Seattle has cataloged more than 100 unreinforced masonry buildings within city limits, older brick and stone structures built without the steel reinforcement that modern codes require. In an earthquake, the mortar holding those bricks together cracks and gives way. Walls lose their structural integrity, and facades can peel away into the street below. In the 2011 earthquake that struck Christchurch, New Zealand, unreinforced masonry buildings accounted for the overwhelming majority of fatalities. In Seattle, those buildings cluster in some of the most densely used parts of the city: Pioneer Square, Capitol Hill, the Chinatown International District, the downtown core, places where an estimated 33,000 people pass through daily as residents, workers, or visitors. The city passed a mandatory retrofit ordinance back in 2019. As of the most recent reporting, only about a quarter of those buildings have completed the required upgrades. More than 600 remain untouched, largely because retrofitting is expensive and the money hasn't kept pace with the deadline. Infrastructure adds another layer to the exposure. Seattle's geography forces traffic across dozens of bridges, spanning lakes, valleys, and rail corridors. The Interstate 90 floating bridges crossing Lake Washington are the only structures of their kind anywhere in the world, resting on massive concrete pontoons rather than fixed foundations. The tunnel that replaced the old viaduct was engineered to modern seismic standards, but its entry and exit portals sit on soil that remains vulnerable to liquefaction. The Port of Seattle, central to the regional economy, sits largely on fill material along the waterfront. A major earthquake wouldn't just damage isolated buildings. It would threaten to sever the transportation arteries that physically hold the metropolitan area together, cutting off neighborhoods and slowing emergency response exactly when speed matters most. Now put the timeline back on the table. Secondary faults within the Seattle fault zone appear to rupture roughly every 350 years. The most recent confirmed rupture on one of these structures likely occurred in the early 19th century. Do the arithmetic, and that puts the region somewhere around 200 years into a 350-year cycle. That doesn't mean an earthquake is overdue in any strict statistical sense. These are irregular, probabilistic processes, not clockwork. But it does mean the region sits somewhere inside the relevant window, at a point where the possibility is neither distant nor negligible. And critically, these are the exact faults still missing from the model that shapes building codes, insurance premiums, and emergency planning nationwide. It's worth being fair to the other side of this story because the picture Angster's research paints isn't purely alarming. A companion study, led by earthquake geologist Elizabeth Davis at the University of Washington and published separately in the journal Geology, approached the fault system from the opposite angle. Instead of focusing on the secondary faults, Davis and her team went looking for more evidence of large-scale events on the main fault itself, the kind capable of an 8-meter uplift like the year 923 earthquake. They mapped more than 150 marine terraces around Puget Sound, measuring depths and estimating how much the coastline had shifted over roughly the past 11,000 years, specifically searching for another event on the scale of 923. They didn't find one. As far as the 11,000-year record shows, the massive uplift event from 923 appears to be a genuine outlier, the only earthquake of that scale in over 11 millennia. That's useful, even reassuring information, because it suggests the recurrence interval for the absolute worst-case scenario on the main fault really is extremely long, quite possibly longer than 10,000 years. But Davis was careful about how far to take that conclusion. Thick layers of accumulated sediment can mask smaller uplift events that wouldn't leave the same dramatic signature in the marine terraces her team was surveying. And smaller, in this context, is a relative term. A magnitude 6.5 earthquake directly beneath a major metropolitan area is not a minor event by any reasonable definition. It simply wouldn't produce the same striking geological footprint that her survey methods were built to detect. Put the two studies together, and what emerges is a fault system that behaves less like a single ticking clock and more like a layered, complicated machine. The catastrophic, once-in-a-millennium event on the main fault does appear genuinely rare. But the medium-sized earthquakes, the ones still capable of killing people, collapsing unreinforced buildings, and severing critical infrastructure, occur far more frequently than the standard models accounted for, and the tools used to guide public policy simply weren't built to capture them. Harold Tobin, a geophysicist at the University of Washington and head of the Pacific Northwest Seismic Network, reviewed both studies without being directly involved in either. His read lines up with that layered picture. The truly massive scenario on the main fault, capable of thrusting shorelines upward by tens of feet and sending a local tsunami through the sound, does appear exceptionally rare, occurring perhaps once in 11,000 years or longer. That's the encouraging half of the story. But the less catastrophic, still seriously damaging scenarios he describes as considerably more likely than previously assumed, and the new secondary fault data is a meaningful part of why that probability has shifted upward. It helps to zoom out and understand the tectonic machinery driving all of this. The Pacific Northwest sits along a convergent plate boundary, where the Juan de Fuca plate, a fragment of a much larger oceanic plate that once spanned a far greater portion of the Pacific, is slowly diving beneath the North American continental plate. This process, called subduction, happens at a rate of roughly 40 millimeters a year, barely perceptible on a human timescale, but immense in its cumulative effect. As the oceanic plate slides underneath the continent, it drags and compresses the crust above it, and that compression builds mechanical stress in the surrounding rock until it breaks. That break is what we experience as an earthquake. The offshore Cascadia subduction zone is where the two plates lock most tightly, building toward the largest possible ruptures. But the shallow inland faults, the Seattle Fault Zone among them, along with the Tacoma Fault, the Olympia Fault, and the Saddle Mountain Fault, exist as a secondary consequence of that same process, absorbing pieces of the stress created by north to south compression, combined with a slow clockwise rotation of the crust above it. As many as 13 active shallow fault zones have been identified across the region, and together they've produced dozens of moderate to large earthquakes over the past 16,000 years. None have ruptured during the historical period, the era covered by written records and seismic instruments here, which only stretches back to the mid-1800s. Everything scientists know about how these faults behave comes from paleoseismology, from reading the evidence buried in soil, rock, and drowned forests. Every new date added to that record shifts the probability calculations a little further, and the picture emerging from the most recent data is more layered and more consequential than the simplified version most people carry around in their heads. There's an irony sitting at the center of all this. Seattle has invested substantial money and years of effort into earthquake preparedness. The Alaskan Way Viaduct, the seismically vulnerable elevated highway that nearly collapsed after Nisqually, was fully replaced by a modern tunnel. Building codes have been revised and strengthened. The Shake Alert Early Warning System, operated by the USGS with state agencies, can now provide 10 to 90 seconds of warning before strong shaking arrives. enough time to drop under a desk or bring a train to a stop. Evacuation routes for coastal tsunami zones have been mapped. Emergency supplies have been stockpiled. But nearly all of that planning was calibrated against the two threats everyone already understood: the offshore megathrust and the rare catastrophic rupture of the main fault. The secondary faults, with their much shorter recurrence intervals, sit in a genuine gap in that preparedness framework. A gap this latest research has made considerably harder to overlook. Washington's Department of Natural Resources currently estimates roughly an 85% chance of at least a magnitude 6.5 deep earthquake in the Puget Sound region within the next 50 years, a 15% chance of a magnitude 9 Cascadia megathrust in that same window, and roughly a 17% chance of a magnitude 6.5 or greater shallow crustal earthquake near the urban core. That last figure, the shallow crustal number, is the one this new research could realistically push upward in future revisions. If secondary faults are rupturing roughly every 350 years, and the most recent known event happened around 2 centuries ago, and these faults have already produced earthquakes as strong as magnitude 6.7, the probability of a damaging shallow crustal earthquake beneath Seattle within coming decades may genuinely be higher than current published figures reflect. Whether these secondary faults eventually make it into the next official update of the National Seismic Hazard Model remains an open question. Angster has said he's hopeful that continued research will produce enough supporting data to justify their inclusion, but updating a model of that scale is a slow institutional process, involving years of scientific review, peer evaluation, and policy debate before any change becomes official. Meanwhile, the faults themselves don't operate on a bureaucratic calendar. The ground beneath Seattle isn't sitting passively, waiting for the paperwork to catch up. It's under constant, ongoing compression. Stress continues accumulating along every fault in the system, from the locked megathrust offshore to the shallow crustal faults threading beneath the suburbs and directly under the city center. That stress has to go somewhere eventually. The only real uncertainty is where it releases first, when it happens, and how severe the shaking turns out to be when it does. None of this is really a call to panic, and panic wouldn't help anyone regardless. What it is a call to update the mental model. For years, the public conversation about earthquake risk in this region has centered almost entirely on the single, dramatic, most photogenic threat, the massive offshore megathrust everyone has seen in documentaries and disaster coverage. That threat is real, and it deserves the attention it gets. But the story emerging from Angster's research is that the more immediate danger might not come from that headline event at all. It might come from a moderate earthquake on a fault most residents have never heard of, rupturing a couple of kilometers beneath office towers, apartment buildings, and century-old brick warehouses, without the decades of media buildup that surrounds the big one, the kind of earthquake that doesn't arrive with any narrative warning at all. It just happens, on an ordinary afternoon, and reshapes a city before anyone fully understands what's occurred. A scenario model built back in 2005 estimated that a magnitude 6.7 earthquake on the Seattle fault could produce at least 1,600 deaths and roughly $50 billion in damage. That model predates everything in this new research, predates the confirmation that secondary faults are this consistently active, and predates the evidence of a rupture as recent as the early 19th century. If that scenario were rebuilt today, incorporating what scientists now understand about how frequently these smaller faults actually break, the resulting numbers would very likely look different, and there's no strong reason to assume they'd look better. The ground beneath Seattle did something the scientists studying it didn't expect. It showed them that the faults everyone had treated as too small to matter are, in fact, more active, more frequent, and more consequential than the standard hazard models ever assumed. That discovery doesn't change what's physically happening underground. The stress was always there, building the same way it always has. What's changed is the level of understanding, the recognition that the danger isn't only the rare, monstrous earthquake everyone has been trained to expect. It's also the medium-sized quake on the small fault nobody was watching closely enough. As of right now, those secondary faults remain absent from the National Hazard Model. Angster and his colleagues are continuing their research. The retrofit program for the city's unreinforced masonry buildings is still behind schedule. And underneath all of it, silently, invisibly, the stress keeps building along every fault in the system, counting down toward whatever comes next.